Welcome to this lecture series in real analysis. Last time we looked at the root test, which was a very convenient and powerful test to decide if a given series is convergent or divergent. It was not an exhaustive test, meaning it may fail to conclude anything, but even if the series is very complicated looking, it might just very easily tell us whether or not that series is convergent. In this lecture, we'll look at another test called the ratio test, which can also be equally powerful depending on the situation. Sometimes the root test is more convenient or useful, sometimes the ratio test is. There are even other tests available, but I don't want to make this lecture series all about testing whether a given series is convergent or divergent. I don't think it serves any didactic. So let's proceed on that note. Here are some problems for practice. And now let us get started. So directly we'll just jump into the main theorem. What does the statement say? Given a series where each term is non-zero, so you're going to apply the ratio test for only certain kinds of series where each term is non-zero, then the series is convergent if this condition happens and divergent if this condition happens. Note that both of these conditions can fail simultaneously. So just like the root test, the ratio test is also not necessarily conclusive. It is not exhaustive. Anyway, so let's prove it and see some applications. Okay, so suppose this lim sup, we are trying to prove 1. This lim sup is alpha and is less than 1. Then we want to prove that the series is convergent. So let beta be such that it is between alpha and 1. Right? And now, by the definition of lim sup, we know that this ratio must be less than beta ultimately. That is, there is some natural number n such that this ratio is less than beta whenever little n is at least capital N. And therefore an plus 1 is less than beta times the absolute value of an. Just applying this thing for little n equals to capital N, then apply that for capital N plus 1 and so on. So we get this is less than beta times an plus 1 and so on and so on. So this gives that this is at most beta times, or okay, I'll explain, beta to the power k times the absolute value of mod n. So how do we get this? Suppose k were 3, then we want to show that an plus 3 in magnitude is at most beta cube times magnitude of an. All we do is multiply all these 3. So what will happen is this will cancel out, that will cancel out. Here you'll see a beta cube, and you see for k equals 3. Similarly, you can prove this for arbitrary k. And therefore, since this is just some positive number, a fixed positive number, we see that this sum is finite, and hence this sum is finite, which implies, call it the comparison test if you like, This is convergent, and that's how we notate it. So that proves this part. And I'm tempted to leave the second one as exercise, but I will not. Yeah, so let's prove the second one. So for this, suppose we have that this is at least 1 ultimately. We want to show that the series diverges. So then, this happens ultimately. And yeah, so what does that mean? So therefore, there is some capital N such that, but note that this also implies that right from here you can easily prove that, because you put capital N in place of little n, then you put capital N plus 1 in place of little n, and then capital N plus 2 in place of little n, and so on. And you will see a sequence of inequalities. We are just saying the last term dominates the first term. Anyway, so just figure this out. And now, since this is a non-zero real number by hypothesis, what we see is that this sequence cannot converge. This does not converge to 0 as k approaches infinity, which implies this does not converge to 0 as n approaches infinity, which implies this series is divergent. Because as we know, for any convergent series, the individual terms converge to 0. And that's it. So that proves our ratio test. And now let's see an application or two applications. All right. So here is our first daunting looking series. And let's just hit it with the ratio test and see if it converges. Clearly each term is non-zero, so we can apply our ratio test. So an is this thing. So what is an plus 1? An plus 1 is this expression, which is equal to that. And now this ratio is equal to that. All right, so now we'll cancel things out. We get this is equal to minus 10 to the 1, which is minus 10 in the numerator. And we also get 4 square in the denominator, which is 16, and n plus 1 divided by n plus 2. So if we take the absolute values, we get this expression. And clearly, in the limit, we need to take lim sup, but in fact, we see that the limit of this ratio is equal to 10 by 16, which is less than 1. Since the limit exists, the lim sup also exists. I mean, lim sup is equal to the limit and is less than 1. So by the ratio test, this is a convergent series. Okay, great. What about the next one? This guy. So again, we'll call this an. So then an plus 1 divided by an is n plus 1 factorial divided by 5 to the n plus 1 times 5 to the n divided by n factorial, which is equal to n plus 1 divided by 5, which clearly is greater than 1 ultimately, greater than equal to 1 ultimately. And therefore, by the E ratio test, this is a divergent series, which shouldn't be a surprise. Clearly, this has much more juice than the denominator. Okay, so some nice applications of the ratio test. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.